Now, whenever we make an approximation, it's highly likely that we're making an error, and the error of approximation is going to be the difference between the true value of the integral and our approximation here. And of course, we don't know what that error is if we're approximating, because if we know what our approximation is and we know what the error is, then we would know the true value of the integral. So it would be a little pointless to try to approximate. So we want to explore ways of controlling our error, or trying to find upper bounds for our error so that we can minimize the amount of error without actually knowing what the error is. Now, for our particular estimates before, we can tell what the error is because we know the actual value of the definite integral up to 100 decimal places if we like. So the error for our midpoint approximation with n equals 6 is the true value of the integral minus the value of our approximation. And here we've included 9 decimal places for each. So we have 1.38629436 minus the approximation we got, and we see our error is 0.00936018. And the error for the trapezoidal approximation is the true value of the integral minus our trapezoidal approximation. And we've written both down here to 9 decimal places. Again, we get it's 1.38629436 minus our trapezoidal approximation with n equals 6. And we see the error here is negative because we over-approximated, and it's negative 0.0190628. So it's a little larger in absolute value than the error for the midpoint approximation with the same number of rectangles. Now, our aim in this section is not to know the exact error, because as I pointed out before, if we knew that, we wouldn't have to approximate, but to find some bounds on the error. You can see that the absolute value of the error is really what tells us how far our approximation is from the true value of the integral. Here we're looking for bounds on the absolute value of ET, which is the error of our trapezoidal approximation, and EM, which is the error of our midpoint approximation. And of course, we're looking at these for some specific value of n. Here we have a theorem giving us bounds for the absolute value of these errors. And we see that the error for the trapezoidal approximation is less than or equal to k, a constant k, times b minus a, the difference in the endpoints cubed, over 12n squared. And the error for the midpoint approximation, or the absolute value of the midpoint approximation, is less than or equal to k times b minus a cubed over 24n squared. And this k, this constant k, is an upper bound for the second derivative of our function between a and b, assuming our function is smooth and has a second derivative. So to use this upper bound for the error, we must find an upper bound for the second derivative of the function on the given interval. And this would involve calculating the function and somehow finding the maximum or something above the maximum on the given interval. Well, let's try to apply this. Let's try to find an upper bound for the error in the trapezoidal approximation of the integral from 1 to 4 of 1 over x dx, where the number of trapezoids that we use is 10. Well, f of x is 1 over x, its derivative is minus 1 over x squared, and its second derivative is 2 over x cubed. Our first step is to find some upper bound for f double prime of x on the interval from 1 to 4. And of course, this will be our k in the formula for the upper bound for the error. Well, this second derivative, 2 over x cubed, is decreasing on the interval from 1 to 4. So therefore, its value at 1 must be the highest point on the function on the interval from 1 to 4. That must be its maximum. So I can use that as an upper bound for f double prime of x for any x in this interval. In other words, 2 over x cubed for any x between 1 and 4 is less than or equal to 2 over 1 cubed, which is 2. So we can use k equals 2 in our formula. And with n equals 10, we have our trapezoidal approximation with n equals 10 differs from the actual value of the integral in absolute value by at most k times b minus a cubed over 12n squared, which is 2 times 4 minus 1 cubed over 12 times 10 squared, which is 0.045. Now this is a conservative estimate for the error, and that makes sense because it applies to all functions. And when you look at the actual difference, the actual error, it's roughly 0.00696667. So we see it's quite a bit smaller than the upper bound given by this theorem. Nevertheless, we have an upper bound for the error, and we have some guidelines as to how far off we could possibly be with our estimate. Just to give you a graphical explanation of how we found this k, remember our function was h of x or f of x equals 1 over x, and its second derivative is 2 over x cubed. And here we've drawn the graph of the second derivative, which is 2 over x cubed, and we see it's decreasing on the interval from 1 to 4, and the highest point on the function is at the left end point. Now all of this we deduced by taking the derivative of this function 2 over x cubed. So for any value of x between 1 and 4, 2 over x cubed is less than or equal to 2. And we can see this clearly from our graph of 2 over x cubed, and therefore k equals 2 gives us a maximum for this function on the interval from 2 to 4. Well, let's try to use our theorem to find an upper bound for the error for the midpoint approximation of this integral from 1 to 4 of 1 over x dx with n equals 10. We've already figured out the k. We know k is 2. And according to the theorem, the absolute value of the error we might be making with this approximation is less than or equal to k times b minus a cubed, this time over 24n squared. So it's clearly going to be a smaller upper bound than for the trapezoidal rule because the denominator here is larger than for the trapezoidal rule. So we end up with 2 times 3 cubed over 24 times 10 squared, which is equal to 0.0225. Now again, this is just an upper bound for the error. It's not equal to the actual error, and more than likely it's quite a conservative upper bound for our error. Now here's another use of our upper bounds. We might want to estimate our integral to be accurate to 10 decimal places or 6 decimal places, for example. So suppose we want to get an estimate which is accurate to within 0.000001, 10 to the minus 6. That is, the difference between the actual value of the integral and our estimate should be less than 10 to the minus 6. let's use the trapezoidal approximation, and here the n is undetermined before we start. We have to figure out which n we want to use to be absolutely sure, using this theorem, that the error is less than or equal to 10 to the minus 6. Well, we know from the theorem that the error is less than or equal to k times b minus a cubed over 12n squared, where k is an upper bound for the absolute value of the second derivative on the given interval, and b and a are the endpoints of the interval. So for our particular integral, the integral from 1 to 4 of 1 over x dx, we've already figured out that k is 2, and of course a is 1 and b is 4. And since our error, according to the theorem, has to be less than or equal to k times b minus a cubed over 12n squared, whatever the n is, if that number is less than or equal to 10 to the minus 6, then we're guaranteed that our error is less than or equal to 10 to the minus 6. So if we choose the value of n, which makes k times b minus a cubed over 12n squared less than or equal to 10 to the minus 6, then we're guaranteed that the error of our approximation is less than or equal to 10 to the minus 6. And of course, the only thing we don't know in this inequality is n, and we can solve for the n. So cross-multiplying, we're looking for an n so that 10 to the minus 6 times 12n squared is greater than or equal to 2 times 3 to the 3. And now multiplying across by 10 to the 6, we're looking for an n so that n squared is bigger than or equal to 10 to the 6 times 2 times 27 over 12. And of course, the square root of the number on the left there is 2121.32. So if we choose n equals 2122, then its square is going to be bigger than or equal to 10 to the 6 times 2 times 27 over 12. And with that n, we're absolutely sure that the error from the trapezoidal approximation is less than or equal to 10 to the minus 6. The actual error is probably an awful lot less than 10 to the minus 6 for n equals 2122, but if we don't know what the error is, and in the absence of any better estimate, we can be absolutely sure that the error is less than or equal to 10 to the minus 6 for this n.